All right, so thank you again, Richard. And also, we will, because of the many laptops, we will have to be ambidextrous here. And what I would like to do is, whoops, that's the wrong one. Sorry, Sarah. Sorry. Let's try this one. Yes. So I would also like to acknowledge the First Nations people, because they were the first scientists and engineers. They were astronomers, they were meteorologists, geologists, hydrologists, botanists, and we do respect their knowledge system as part of the oldest living culture on Earth. So for times almost, if you pardon the pun, immeasurable, people have asked questions like how tall, how far, how long, how bright, how hard, how much, how sweet is something. And this example here is from the valley of the river Nile, where people needed answer to these questions as they observed, for example, the flooding of the river. They determined when to plant and harvest crops and to build these structures, these enormous structures that we can still see today. And also as they had to organize quite a complex society. So asking these questions and trying to answer them is often trying to relate to the world that surrounds people, and this is in many cases a very personal process and a very localized experience. And so people have for a long time used their own bodies as one of the tools to establish, in this case, length measurements. So the width of a thumb, or the length of a foot, or the span of your arms, or the length of someone's stride. And they also relate some measurements to their daily economic activities, if you like, such as in this example in agriculture. So, for example, the length an ox could pull a plow was the furlong, or the area that could be plowed in a day by a team of oxen was an acre. And again, those measurements could vary depending on where you are, because the character of the soil would determine that to some degree. Here's another example. This is the Finnish equivalent of our sheepdog, the Finnish Lapphund, used for herding reindeer. And in Finland, there's an old unit of length called the peninkulma, which is the distance over which the bark of the dog can be heard. So this is about 6 to 10 kilometers or so, and again derives from a practical need that people had every day. So why should we talk about measurement? Well, I'm terribly biased, but I think it is, because it permeates our lives, it's everywhere. It makes things work, but also it's an important tool for innovation, for discovery. So just as an example, I use this. So we come together here, and there's measurement that actually made this possible. We may have used maps, we may have relied on a global navigation satellite system like GPS. There may have been traffic lights that directed us, and the color of those is important. You need to measure it to make sure they're safe. People may have looked at speedometers, at fuel gauges. You may have filled your car at a petrol pump or charged it at a charger. Measurements everywhere. You may have gone through a speed camera, or perhaps even encountered a breathalyzer. So there's measurement for all of these things. So the technology that moves us, that connects us, the food we eat, the medicines we take, measurements are essential in producing these things, hopefully effectively, and also trading them, and hopefully fairly. I'll give you a couple of examples about the bit I said about the importance of measurement in discovery and innovation. So this is the observatory of Tycho Brahe, a famous astronomer. So this was called Uranienborg on the Danish island of Ven. And we see all kinds of measurement instruments here. For example, the large mural quadrant, and importantly also, in the bottom right, a clock. And it's his very, very accurate observation of celestial objects in the 16th century that were used by his mate Johannes Kepler to develop his laws of planetary motion. So without these exact measurements, that wouldn't have been possible. Here's another example where accurate measurements supported, if you like, a revolution in scientific thinking. This is an optical interferometer. It was invented by Albert Michelson and used in a very famous experiment with his colleague Edward Morley in 1887 to discover that the speed of light was the same whichever way you pointed it. And without going into any technical details, this was critical for Albert Einstein to develop his theory of special relativity. So without this experiment, or this experiment was a critical contribution to that development. And here's a modern day example that's very closely related, because it's the same technology, just developed and further refined for about a century and a bit more, which is the Laser Interferometer Gravitational Wave Observatory, also known as LIGO. And in 2016, this facility achieved the first detection of gravitational waves. They did this by measuring very, very tiny changes in the length of these two perpendicular arms. Physics Nobel Prize in 2017, very shortly after. Gigantic progress enabled by precision measurements. So then why also talk about measurement now? Well, 150 years ago, almost to the day, it was 12 days ago actually, was the 150th anniversary of the signing of the meter convention. So that established the system that we use still today to measure things. 17 nations signed it at the time, and it's one of the oldest international treaties that's still in operation. And as the name suggests, the meter convention established the metric system as the base for our measurements, base units of the meter and the kilogram for measurements of length and mass. Australia joined in 1947, and today there are 64 member states of the convention and 37 associate states and economies. And even if there's some holdouts, the metric system is today adopted for everyday use almost universally. So the 20th of May, which was the day the meter convention was signed, is now World Metrology Day, recognized by UNESCO. And metrology, by the way, should not be confused with meteorology. Although meteorology does depend on measurement very critically, actually. And speaking of UNESCO, this is my colleague Victoria Coleman on stage at the UNESCO event a couple of weeks ago at the official celebration of the 150th anniversary. Something we all are proud of. Victoria is a member of the International Committee for Weights and Measures, the CIPM, which is one of 3 international bodies that the convention set up. The first one is the General Conference. It's a bit like the stakeholder meeting of a corporation. Second is the CIPM I just mentioned, which steers the technical work in the different areas of measurement science. And the third is the International Bureau of Weights and Measures, which the BIPM, which resides in a lovely chateau in Sèvres, just in the west of Paris, and is responsible for the coordination and administration of the system, including as the custodian of some of the established global measurement references. And here's another incarnation of that building, again from the celebration 12 days ago. So what then is a measurement actually? I describe it as a comparison of an observation with an agreed reference. And to illustrate this, here's my boss, Bruce Warrington, Australia's chief metrologist, and his boss, Helen Wilson, the Deputy Secretary of the Commonwealth Department of Industry, Science and Resources, and she is determining Bruce's height. And the agreed reference here is a tape measure. But all the components of the measurement are there. So what should these agreed references actually look like? First of all, they should be fit for purpose. This is the old #1 imperial standard bushel of the Queensland government. And this valuable table for businessmen from 1854 shows across the top, it's probably hard to read for you, a bunch of different agricultural products measured in bushels. So this reference served a very practical and important purpose in trade. The table also shows that there certainly was a distinct lack of consistency between the different jurisdictions, in this case in the United States. The second desirable feature of an agreed reference is that it should be constant, no matter when and where someone makes a measurement. And you can possibly see the title of the talk starting to come through. For example, the rotation of the Earth was considered a constant and was used to derive time references. And finally, the agreed references should be accessible. And so here's a younger version of me illustrating accessibility of a medieval length standard. This is an iron bar embedded in the wall of a church in Nuremberg, in Germany. This represents 6 Nuremberg working feet, about 1.67 meters, the whole thing, and this was used in the construction of churches and for gravestones. With that comment on accessibility, the important role that these references played in organizing societal interaction is also about exercising asserting control, and therefore has often been the privilege of those in power. For example, to come back to the ancient Egypt and the Nile, this is a Nilometer, an indicator of the level of the river, calibrated in Egyptian cubits. And this was, as I said before, a crucial tool to help predict what the river was doing. And was important, for example, to set levels of taxation for the year. And access to these indicators was restricted. So priests and rulers could access them. In some cases, they were actually installed in cisterns within temple compounds that were off limits to the general public. So setting standards for weights and measures has been often the privilege of sovereigns and states. A couple of examples: the Magna Carta of 2015. I won't read the clause that says that everyone should use the same measure. The other example on the right is our very own National Measurement Act, which actually says, it specifies how the Commonwealth executes its constitutional powers on weights and measures. Also defines the role of my own organization, the National Measurement Institute, in ensuring that, as Richard says, measurements here in Australia are fit for purpose, are accurate, and are internationally recognized. So the powers that be, since they had the power, went ahead and set standards for measurement. Results was a proliferation of different measurement standards in different jurisdictions. Here's an example, which is a set of 71 weights collected by British consuls between 1818 and 1820 on the order of the Foreign Secretary. And in some places, even more complicated, even if you were in the same place, different standards for weighing, for example, was used for different goods, such as precious metals, medicines, or salt. For length, the situation was similarly Babylonian. So this is from a template from Talleyrand, and it shows a multitude of different weights and measures used in France at the time, where the situation was particularly bad. So there was a need for universal standards for length, and a standard that's fit for purpose, constant and accessible. The two approaches that were most favored were a pendulum, whose period is about a second, which gives you about a meter in length, and a specific fraction of the meridian of the Earth, so the shortest curve between on the Earth's surface connecting the poles. And you see, in this illustration, those two tools. So the French, despite efforts in Britain and in the US to establish a system of such standards based on the metric, what we now call the metric approach, the French, who had also looked at this opportunity, pushed on. And while they didn't follow the proposal to use the pendulum, they did decide that the meridian method should be used to implement measurement reform. They had a committee of very famous mathematicians, including Laplace and Lagrange, and they recommended that both decimal division of weights, measures, and length, weights, length, and money should happen. But they also decided that the length standard should be based on 1/10,000,000th of the distance from the pole to the equator along the meridian that passed through Paris. And by doing this, for the first time, they intended to have a system of measurement that according to the then Secretary of the Academy of Sciences, should be there à tout le temps, à tout le peu, for all times, for all the people. So they established a provisional standard based on some earlier measurements, meridian measurements, and distributed copies of this provisional meter throughout France. Here's an example that's in Paris. And a couple of Frenchmen, Jean-Baptiste Delambre and Pierre Méchain, went on a mammoth endeavour to extend the existing measurements of the meridian arc from Dunkirk all the way to Barcelona, and I'll say no more about this. Once they were done and established that way a value for the new unit meter, 2 platinum and 12 iron standards were fabricated, and also a 1 kilogram mass standards based on this length standard, which represented a cubic decimeter, so 10 centimeters, on all edges of distilled water at its ice point. That gave you the kilogram, and so again, the equivalent mass was made out of platinum, and they were deposited in the French National Archives and were known as the kilogram and the meter of the archives. This was in 1799. The standard for time, as I said before, had long been established from astronomical observations. The sexagesimal system, base 60, that the old Sumerians had used, was established, and that's where we got our 60-second minute and 60-minute hour, 24-hour day. The Jacobins tried the decimal time division, but that didn't go anywhere. And speaking of timekeeping, I couldn't help myself but putting a picture of this turret clock in St. Luke's in Bothwell that I have the great pleasure to wind every Monday night together with John Fowler. Thanks, John, for coming. So, as the 19th century went on, the elements for this new measurement systems were coming together. There were some famous scientists such as William Thomson, who was later Lord Kelvin, and James Clerk Maxwell, and you can see both of them in this picture behind Nobel laureate Bill Phillips, taken at the celebrations a couple of weeks ago. And they proposed that based on these new achievements, a system of measurements for base quantities of length, mass, and time should be established and should be decimal. And so this system, as we've seen, was formally adopted 150 years ago. International prototypes of the meter and the kilogram were produced, and they were and are kept at the BIPM in Paris. They made 31 meters and 40 kilograms. The ones closest to the existing meter and kilogram of the archives were declared the prototypes, and the others were distributed through, by lots to the signatory nations of the convention. So this sits, these sit in a basement, in a vault in the basement of the BIPM. The vault can only be opened by 3 different keys held by 3 different officials independently. And in the middle you see the international prototype, the famous Big K, and a few copies. We have copy number 44 in Australia. This is Barry Inglis, the first CEO of the National Measurement Institute, and he was also once the president of the CIPM. And so this initial system of quantities and the corresponding units was then extended over the next decades. We added the ampere for electric current, the Kelvin for thermodynamic temperature, the candela for luminous intensity, and then in 1960 the system was complemented by rules for prefixes and for derived quantities. And it was also importantly named the International System of Units, the SI. And then in 1971 was extended by the unit for the amount of substance, the mole, which brought this vast universe that is chemical and biological metrology into the system. So here we have it, a universal, internationally agreed system of fundamental units based on comparability and mutual recognition. But there was a problem. We still hadn't realized the ambition to have references that are, in the words of Sir Riggs Miller, the British proponent of the metric system that didn't go anywhere in Britain, not from any work of art and capable of being regenerated by an observation taken from nature at any distance of time and place. In other words, for all times and for all people. We still had fundamental quantities defined through artifacts of limited accuracy and possibly also limited durability. So how to improve the situation, scientists had pondered for quite some time. And the progress in understanding the properties of atoms and their description by theories of electrodynamics, thermodynamics, quantum mechanics allowed to find ways in establishing alternatives. So the structure of the atoms and observing how atoms absorb and emit light of distinct colors or distinct wavelengths that are characteristic of different chemical elements were important in this process. And the same process gives us the striking colors of stained glass windows, such as those here in the rose window in Chartres Cathedral in France. So these wavelengths are very unique properties of atoms and therefore make excellent rulers at the micro and nano length scales. And in addition, work of scientists such as Maxwell, Kelvin, Boltzmann, Millikan, Planck, Einstein, and others also showed that the behavior of matter at the atomic scale can be described in theoretical models that feature universal constants, such as the speed of light, the elementary charge, the Boltzmann constant that links thermal energy and temperature, and the elementary quantum of action, the Planck quantum. And so it was desirable, therefore, to express the units of measurements in terms of such constants, which, as far as we can tell, are that constants across the extent of space and time that we can ascertain as humans. And as Planck noted, these would be not only for all people, but for aliens too. So the first artifact that was replaced here was the meter. So it was redefined in terms of the wavelength of a specific atomic transition. The prototype was gracefully retired to its vault at the BIPM. In 1967, following the development of atomic clocks, the astronomical definition of the second was replaced again by multiple of a period of a particular wavelength of electromagnetic radiation associated with an atomic transition in the element cesium. These are the cesium atomic clocks at the NMI in Sydney that keep the time for Australia. And in 1983, the meter again was redefined as the distance traveled by light in a particular fraction of a second. So this is an example where one base unit, the meter, depends on another one, the second. And because frequency, the inverse of time or time interval, is the most accurate thing we can measure, to a few parts in a billion billions, we all bow to the time laws. And after decades of really intense scientific effort, the global metrology community developed two independent methods to realize a new definition for the kilogram at an accuracy that was sufficient to replace the international prototype. The first measured method that you see on the left uses an electromechanical balance. This example is the one built by our colleagues in the US, so-called Kibble balance, and it compares mechanical and electrical power. The second method, known as the X-ray crystal density method, determines the mass of a pure substance from the number of elementary elements in that substance and from the mass of one of those elementary entities. And this is Achim Leistner from CSIRO with a near-perfect sphere of silicon that was used as part of these experiments. And so by 2018, with electrical and thermodynamic quantities now expressed in units defined by constant of nature, we were ready for a major revision of the SI. It was formally decided on the 26th meeting of the General Conference, and it finally retired big K and defined all units in terms of such constants. And this, together with guidance on how to practically realize those base units, provides a recipe that anyone can use anywhere at any time. And this is finally fulfilling the ambition for all people for all times. So does that mean that everything is settled and that we're done? Not really, because science and technology advance all the time. The needs of researchers, businesses, and the community for more accurate and accessible measurement also increases all the time. And global challenges around us require new solutions, and measurement science needs to keep pace with that. We don't have to look very far to see an example. In fact, we heard about it in Professor Nathan Bindorf's lecture earlier this year, when he talked about how scientists monitor and model the changes in the Antarctic ice cap in the Southern Ocean. Now we'll use the example of length measurements because they're relevant in addressing serious challenges we heard about in Nathan's talk. This picture illustrates the broad scale over which these measurements need to happen. There's a factor of 100 million in scale between the objects, between adjacent objects here. 10,000 kilometers for the Earth, about a tenth of a meter for the football, and a nanometer or billionth of a meter for the carbon-60 molecule on the right. So, very brief look at the two extremes. The global scale, the example is the Gravity Recovery and Climate Experiments, follow-on mission, also called GRACE. And Nathan did mention this in his talk because it tracks the movement of water on Earth by measuring local variations in gravity. So this way you can look at changes in underground water storage, amount of water in large lakes, rivers, soil moisture, and ice sheets and glaciers, and also sea level caused by the addition of water to the ocean. The way this GRACE mission does this is by constantly measuring very minute variations in the distance between orbiting satellites using the same technique we saw earlier with the examples with the LIGO experiment, but now over distances of about 200 kilometers. At the other end of the scale, we need to measure very accurately length in the atomic realm. This is important for manufacturing of components for quantum technologies, for example, to develop advanced materials with novel properties, and to help researchers better understand unique phenomena that happen at these small scales. This allows us to have more computing power for modeling complex processes such as those that Nathan described in his talk, for designing energy efficient, environmentally friendly materials, and for characterizing the atomic scale components that are required, both as part of the design but also during manufacturing. So this is a machine that we built at the NMI that also uses laser interferometry, but this time is to make measurement in a way that is directly traceable to the definition of the SI meter at the nanometer scale. And so, in essence, this machine allows us to make rulers at the nanometer scale. And so, this is an example of such a ruler structure, amplified or magnified 1 billion times in a very nice immersive visualization facility at the University of New South Wales. Another important area for the future of metrology, the science of measurement, is digital transformation. And the CIPM, the committee I mentioned before, has an important initiative about the SI digital framework to develop and establish a worldwide uniform and secure data exchange format based on the International System of Units. An important feature of that initiative is that there's an emphasis on what's called the FAIR principles for data management and stewardship, so that data is findable, accessible, interoperable, and reusable. So the future also in measurement science is digital. And finally, the clock is ticking for the second, literally. This is an ytterbium lattice clock at the National Institute for Standards and Technology in the US. The performance of clocks like this has now reached a level where we are making plans for a redefinition of the second. There are completely new applications that this will open up, including in astronomy and geodesy, but also it will hopefully allow us to test with greater precision our assumption that the fundamental constants that we use to define the International System of Units are indeed constant. I finish with 3 quotes. The first one is from Stephen Chu, who is a fellow Nobel laureate to Bill Phillips, who you saw earlier, and a former US Secretary of Energy, and I won't insult your intelligence by reading it to you. The second is from Lord Kelvin. And the third one is actually on my chest, but it's probably too dark for you to see. It's a quote by the German poet Johann Wolfgang Goethe, and what it says in German here, in English roughly says, "With knowledge grows doubt." I leave it there, and I went too long, sorry about that.
Totally fine.
Over to you, Sarah.
Thanks, Jan.
Thank you all for coming today. It's a real honour to be here, and thank you, Jan, for inviting me to speak with you on a topic that's very close to my heart, measurement, which may be a little bit unexpected for an artist, but follow me on this journey. Okay, now is it going to let me change? Excellent. So I'm a conceptual artist with an interdisciplinary practice that reflects critically and poetically on the matter and methods of science. I'm interested in the systems and structures that shape the way we see the world. I'm particularly interested in the tools of measurement and concepts such as maps, rulers, clocks, and calendars that have the capacity to operate as both scientific and cultural apparatus, that exist because we collectively believe in them and use them, I would argue, performatively to negotiate our understanding of the world. Part of that performance, I suggest, is the sense of precision, accuracy, and determinacy that they offer, which is both at once real, but remains slippery, speculative, and whimsical when tested in the field. I often refer to a quote by social theorist John Culkin: "We shape our tools, and thereafter our tools shape us." And as an artist, I'm constantly trying to illuminate this dynamic, to consider both the reality of how our systems have been constructed and how they might be different. Okay, here we go. My work is often an interplay between art, science, and philosophy, an interplay that Deleuze so beautifully described in his essay, Mediators, highlighting the tension and opportunities that such actions afford. What I'm interested in are the relations between art, science, and philosophy. There is no order of priority amongst these disciplines. Each is creative. The true object of science is to create functions. The true object of art is to create sensory aggregates. And the object of philosophy is to create concepts. From this viewpoint, given these general heads, however sketchy, of function, aggregate, and concept, we can pose the question of echoes and resonances between them. How is it possible, in their completely different lines of development, with different rhythms and moments of production, how is it possible for a concept, an aggregate, and a function to interact? I think that in making art specifically about measurement, that this is the question, this tangled ecology, and I'm constantly trying to unpack it. Over the years, I've done this in numerous ways, specifically in the context of distance and its measurement. I've created a map on the scale of 1 to 1 that was installed in the space that map represented, playfully engaging with George Louis Bourges and Umberto Eco's on the impossibility of drawing a map of the empire on a scale of 1 to 1. I have a lifelong performative drawing work in which I record the distance the moon is moving away from the Earth, which is approximately 3.78 centimeters per year. I have created a series of sculptures of mountains using a length of twine that is the height of that mountain, and created performative drawings in which I've attempted to draw a meter by sight, an act that continued until this was achieved. And through these works, I aim to demonstrate that measurement is both an idea and an action, constantly understood and negotiated in relationship to the body. This idea of expressing measurement as a tactile and active concept has a long history in conceptual art, so beautifully expressed here in this work over 100 years old by Marcel Duchamp called 3 Standard Stoppages, in which Duchamp dropped a meter length of string from a meter height 3 times to create a related yet independent standards. Similarly, there is this work by Walter de Maria, a broken kilometer, which is a visualization of 500 2-meter bars, making a kilometer a physical, experiential, and emotional experience. This work is permanently installed in New York City, And when you go into the room, you feel the vibration of length. You understand it in a very different and emotional way that you don't calculate when thinking about measurement typically. And then there's also Mel Bochner, who activated measurement as a temporal, living, and playful entity. While it may not be immediately obvious that these works possess a direct relationship to science and scientists, they all in fact have a very unique and direct relationship to scientific inquiry. Deschamps made 3 standard stoppages in response to Poincaré's work on non-Euclidean geometry, and Bochner began his measurement series at a time when he was an artist in residence at the Singer Laboratories, where in an effort to find common and communicable language with his scientific counterparts, the act of measurement struck a chord. And here's this wonderful quote by him. As time went on, the subject of discussion kept coming back to how communication could be objectified, which boiled down to the issue of measurement. That's when measurement as an idea entered my thinking, because it's only form of verification that scientists would accept. If they didn't have a measurement and it wasn't repeatable, then they feared ambiguity could creep in. I wanted to show them that measurement itself is not immune to ambiguity. So one day I came in early with some letrocept numbers and black tape and randomly put up different measurements around the lab, not attached to anything, just 3 floating on the walls, on the doors, on the floor. I didn't tell anybody what I had done, so when they came and discovered them, it brought a whole new round of questions, starting with, what does it mean to divorce measurement from an object? This led to the ultimate question of skepticism. How much trust is embedded in objectivity? I will freely admit my trust in this objectivity was, for most of my life, absolute. I had never really considered what the world would be without it. My own engagement with this kind of questioning came through this artistic practice, and specifically relating to the meter, where I had this moment of recognition that I didn't really know much about what the meter was, how it came to be, and the extraordinary efforts that brought it into being. It was simply a ubiquitous tool I had known my entire life that I accepted as is. I had not really considered that there was a point before the meter and that there was a solution to a problem, where Paris had become a centre of trade, bringing with it measuring systems from across Europe, and where there had been an excess of over 2,000 types of measurement in operation, one for each material, with each regional producer using their individually devised system of measurement, causing absolute chaos in the capital. Louis XVI, in one of his last acts as king, decried this as unsustainable and commissioned 2 French astronomers, as Jean mentioned, Etalon and Machin, to devise a new universal system that would be French, of course, but marketed as a global tool and a system for all. In response to this, they undertook a grueling 7-year geodesic survey of 10 degrees of the Earth's latitude, measuring the distance between Dunkirk and Barcelona. From this, they could determine the Earth's size accurately for the first time, creating a standard measure that was 1/10,000,000th of a quadrant of the Earth, which remains the foundation of the metric meter that we use today. Now, this story was not taught to me at school. This was not brought up, this was not communicated, and I never really understood the meter to be a unit that was directly bound to the Earth. I thought this was beautiful, poetic, and clearly an artwork waiting to happen. So I wrote down my dream score for an artwork to be, the idea that I would walk an arc of the Earth and measure it for myself to create my own meter. Little did I know when I wrote those words that only 2 years later, after walking 2,100 kilometers across 112 days, I would have remeasured the Earth for myself and made a meter of my own. While the original exhibition had not been undertaken by foot, I knew as a performance this work needed to be walked. I wanted to know what it felt like to walk this arc of the Earth, physically to know what this measure was, and for my actions and my body to be measured against it. To accurately measure the Earth, I created a real physical experiment that would result in a new meter length. I collaborated with my husband, mathematician Dr. Darren Ngueta, who devised a lightweight experimental system using GPS, a laser rangefinder, and a custom target that could be set up whilst walking. The idea was that at least one field measurement would be taken each day, and by applying the Haversine equation to this data, we could estimate the Earth's size and average the results to build a new meter length. This work was not completed in isolation. Early on, I realized that in order to be able to undertake these experiments out in the field, I would need assistance. And if I'm honest, out of safety, I decided I'd have a walking partner who would be a companion, a collaborator, and 2 points that defined a measured length. So I did what is often done when working on these kinds of projects as an artist. I did a social media call out. I asked if anyone would be interested in joining me on a walking project that was still being worked out at the time. And overwhelmingly, I was contacted by female artists and creative practitioners. And this very organically became a foundation of the work, which really came into focus as I came to name the project, Etalon, which means both standard of measure and stallion or male breeding horse. I love the etymological bind of these terms and saw it as an opportunity to actively reclaim the history of scientific expedition and experience reframed through the female lens. I ended up being joined by 11 companions over 14 weeks of walking. I walked between 15 and 35 kilometres per day, determined by the landscape, my companion, and the basic realities of walking across a country, trying to access food and shelter. We walked 6 days a week, with every Saturday a transition day between my walking partners, which functioned as a handover and an opportunity for me to rest, reset, and get any necessary supplies. There was no predetermined path rather than the guidelines established by Etalon Machin, and we would map out a route and navigate the landscape as we found it, often proving different from what Google Maps suggests. I won't lie, it was extraordinarily beautiful. Bucolic in all the ways you imagine the French countryside to be. We crossed over established walking trails like the Camino, and I got to have my own Caspar David Friedrich moment, standing at the foot of the Pyrenees. We measured the world as we encountered it. But within all of these beautiful rural scenes, there also came the industrial spaces, the edges of cities that no one invites you to see. To my mind, these too were beautiful, but many were also just banal and nondescript. And unlike the hiking trails or predetermined design for pleasure, you simply had to walk through them regardless. I often encountered areas not designed to be walked through. And I came to recognize how much of our landscape is now designed to be accessed by car and car alone, and how the simple act of slowing down and moving to and from a place on foot intimately changes your understanding of how our modern world is constructed. The act of walking day after day is physical, and sustaining a project of this size is hard. And I wanted to share some thoughts of some sentences of things that I wrote whilst on the road. They were short because it was difficult at the day's end to come to sit down and write. This is it. This is what it feels like. I thought through the act of doing I'd find clarity, a sense of resolve. Instead, I've gained bruises and blisters and a crippling anxiety. Is it possible I know less now than when I started? What have I done? What am I doing here? I've adjusted to the physical pain, but I'm struggling with the mental anguish. In the end, it is time as it is, unvarnished. It all feels precarious, teetering on the edge of oblivion, stitched together by a rapidly fading notion that an idea can overcome any obstacle. The rawness and inexactitude are mind and map laid bare. There are no guarantees besides walking and measuring. All else is indeterminable. You must measure and be measured. I cannot tell you what comes next, except steps, one after another, making no more than an inadequate trace, an invisible line from sea to sea. The landscape changes and I change with it. I'm clearly out of my depth, in over my head, excruciatingly exposed. I'm constantly viewed through the prism of others, judged for my capacity to sustain, control, to quantify an experience. There could never be more than a frame for this, an untested scaffold. I brought you along for the process of building, the messy and imperfect act of assuming form. I feel I must alleviate your hurt, your aches, your discomfort, yet there is no mechanism for this. This is the work. The force and constraints in constant motion, the uncontrollable, the elemental, the emotional. The work is all of these things for me and for you also. An accumulation of emotion, thin skin rubbed raw. The bind of actions within actions. You cannot rest, you cannot stop. This is it. This is what it feels like. In the strangest way, the work ended just as I was getting ready to begin. I reached 100 days and around 2,000 kilometers and suddenly felt capable of walking the distance that I had to, just as I crossed the border between France and Spain. By that point, my body was so used to walking, I wanted to keep going. I was ready to tackle another 1,000 kilometers, another 100 days. So it was a strange mixture of overwhelming emotion, relief, and palpable sadness when I realized I'd somehow reached Barcelona and this was all coming to an end. I was rejoined by one of my walking companions who flew back to Barcelona to see me on my last day, and this was me arriving at the beach as everything finished on 112 days, just over 2,100 kilometers. And I have to say, the grief of that moment and the act of finishing it lasted much longer than the walk itself. It took me more than a year to recover from the process of making it. Subsequently, though, it has now become an archive and an exhibition and an object outside of myself. And it has been exhibited both in Newcastle and in Bathurst in a large-scale form. To strategies for dealing with an archive of this nature is no mean task. It's not finished. I don't imagine it will ever be finished. But I've landed in different strategies of showing the work and showing how do you capture 112 days of content into an exhibition form. This is a series of images that I made week to week, where it's a meter-long print with a horizon line that stretches through the 6 days of walking, with additional images that appear and disappear depending on the chaotic nature of the act itself, of how the walk transpired. In addition to walking and measuring the earth, I also had another daily task, which is to write field reports on these custom letterpress field notes that were sent back to Paris to the director of the Musée des Arts et Métiers, France's preeminent scientific museum, where the historical forms of measurement are kept on site, and it was the location of the original foundry where de Longchamps meter was made. So I wanted to have this relationship with a scientific institution, send notes from the field. These included my measurements every day, a Polaroid, and information as you see. So the distance walked, the weather, my emotional state. And these were received by Eves and displayed in the museum as they arrived. So it was a literal display of my walk that was carried out throughout the process of creating it. Here was a particularly good day when the marker read both Barcelona and Paris, way up in the mountains in the middle of nowhere. And these are now exhibited in the exhibition, and I actively walked through as part of the work. It was very important to me that they were displayed in a long line, forcing the viewer to walk with me to measure themselves against the work, and have been constantly surprised at how much time and effort people put into reading the entire journey. One other element is this black and white sculpture that you see here, which are the 108 measurements that I took as part of the performance, my provisional meters. So each day I would take a measurement and get a length. These are between 997 millimeters and 1012 millimeters, slightly varying in length at the ends, representing that kind of calibration of accuracy to determine my meter length. And these have been displayed in multiple ways, so inside the gallery and inside this space at the lockup in Newcastle, which is a gorgeous space. It was originally a police station that has this beautiful kind of calibrated roof that reflected really nicely off the work. Then they are displayed alongside both the physical photographs and objects from the walk. This was my walking stick, which broke around day 101, crossing over the border, along with a set of maps that I carried in my pack. My pack weighed about 20 kilos for the entire performance. Not what I would recommend for hiking these kinds of distances, but if you want to make an artwork, you make sacrifices. And on these maps, both myself and my companions would write the notes that we remember from the road. So this incredibly specific emotional experiences or little reflections on the landscape. And last but not least, my meter, which in its length is 100.02 centimeters, which is more accurate to the size of the Earth than the original meter. And so that's end to end, as the original meter bar was made, with my journey mapped in the middle. Really trying to reflect on the concept that these metrics that we use and think about as end to end, they have stories and lives in between them, and they exist as real lived experiences. As much as John was saying, that they're not just a static thing, that they have an emotional cadence to them. And I guess lastly to leave off is what came next, which was a sort of an extension of this thinking. After making a sort of an effort to understand the meter here on Earth, I started thinking about the meter as it might exist beyond Earth, and how do we understand measurement outside of our planet? And this work, Metric Units of the Solar System, was taking the fundamental principles of the meter being a metric made against the size of the Earth, and using that principle to set a meter length for each planet in our solar system. So it's Mercury, Venus, Earth going down. Jupiter is the length of about 12.5 Earth meters. And Pluto, which I still consider a planet, although that is contentious, is all of 18 centimeters long. So yeah, I thank you very much for listening to my talk and bringing a different perspective on measurement.
So maybe just thank both Jan and Sarah for two different passionate talks from two very passionate people about their subject. So thank you again for entertaining us for the afternoon, by giving us lots of insight into measurements and people and time.
Thank you so much.